students. So continuing our lectures on electronics, we will first start with emitters and antennas. This topic comes under the heading of acquisition of informations. That's basically acquisition of information. Now, nanotechnology plays an important role in improving the performance of individual sensors. And in manufacturing high-performance sensor arrays, it also facilitates integration of sensors with other information processing components, and also allows deployment of low-power sensor systems in previously impractical applications. Nanotechnology gives designers powerful means of tailoring the electrical, optical, and magnetic response of sensors for modifying sensors' external characteristics to ensure compatibility with endurance amidst its operating environment, and for implementing advanced sensing algorithms utilizing multiple interconnected interacting devices. Nanofabricated antennas and emitters can be designed to efficiently couple light into or out of devices across electromagnetic spectrum. So now we are coming to nanofabricated antennas and emitters. We call it A and E. Designed to couple light into or out of the device according to the electromagnetic system. So there is a device, and light either it's into or out of this device according to the electromagnetic spectrum. They will be utilized in transducers to facilitate like high sensitive spectroscopes. The main object it uses in transducers. For highly sensitive spectroscopies. The low noise, low signal performance of nanostructured magnetic sensors is access to giant magnet resistance. So we can have information that there is a low noise, then low signal performance, of nanostructured magnetic sensors has access to nanostructured magnetic sensors. They are success to giant magneto resistance. In channel vent resistance, what is the main component is the reed heads, and it actually continues to improve. Nanostructured materials continues to improve the reed heads, and they become a critical part of the spintronic system. So we're talking about GMR, which actually is a part of spintronics. And the reed heads are a major component of it. And apart from this, nanoscale chemical or biological detectors responding to individual molecules or given species will be also an added advantage. So, nanoscale chemical and biosensors and they respond to individual molecules, respond to individual molecules of a given species will be common in space. This sensitivity will be paramount importance in designing medical interventions at the molecular level and also responding to biological or chemical hazards. So there is a medical device, or in case of chemical or biological hazards, these devices will come in handy. Now, there are many enabling technologies for nanoscale acquisition, for nanometric light sources and nano antennas. Essential building blocks are nanophotonic sensors. So you consider nanometric light sources and nano antennas. If we consider these then for that, the essential building blocks for nanophotonic sensors. These are the essential building block of nanophotonic sensors. And they are mainly suched in the form of semiconductor quantum dots or plasmonic nanostructures. To couple with optical wavelengths to a smaller nanoscale device. These are done to couple with optical wavelengths to a smaller nanoscale device, to a nanoscale device. Now these approaches offer efficient tunable coupling across much of the electromagnetic spectrum. They can be used with electro-optical transducers to enhance spectroscopic techniques including Raman scattering, fluorescence, resonance energy transfer, and surface plasmon enhanced fluorescence. So there are some spectroscopic techniques or spectroscopic phenomena that will take place, and optical phenomena like you can have Raman scattering, or fluorescence. Surface plasmon resonance. And also it has been seen that nanostructured probe tips can improve the resolution of the near field nanoscopic imaging tools. Can improve resolution. Natural and artificial nanopores and nanotubes are additional enabling technologies useful in variety of nanofluidic biosensors. So there is a natural and artificial nanopores or nanotubes. So these will be helpful in nanofluidic biosensor and molecular electronic devices. Now, coming to the emitters and antennas, let us start with that. Now, so antennas and emitters. Now, Semiconductor quantum dots, call, call them as QD. Semiconductor quantum dots have electromagnetic properties that can be tuned via quantum size effects. So its properties are pretty tunable. Electromagnetic properties, and this tunability comes from the size. Now, two independent classes of semiconductor quantum dots have merged with considerable potential for advancing nanoscale processing, communication, and sensing, where they can be used as nano antennas and nanometric light source. These are epitaxial Allen quantum dots. So this one is called epitaxial island quantum dots. This is the first one, and these are formed on crystalline substrates such as indium arsenic gallium arsenide or germanium solid. So they are formed on crystalline substrates, and the examples are indium arsenide formed on gallium arsenide, or germanium on silicon. Dubbed self-assembled quantum dots. It's called self-assembled quantum dots. Self-assembled quantum dots. And apart from that, we have another type of quantum dot called colloidal nancrystal quantum dots. Colloidal nanocrystal quantum dots. It's called NCQDS, and examples are zinc selenide ZNS, H-form in solution. Now, self-assembled quantum dots have been incorporated in ultra low threshold and high speed lasers. So SAQDS, they are used in ultra low threshold and high speed lasers, and long wavelength infrared detectors and long wavelength IR detectors. These advanced devices are already competitive with established quantum well-based devices and hold promise for significantly high performance. Now, in contrast, the colloidal nancrystal quantum dots have primarily been utilized as improved luminescent levels for biological molecules. So we talk about NC. Let me use a different color. We're talking about NCQDS. So they have been utilized as improved luminescent labels for biological molecules, improved luminescent levels for biological molecules. And cells in solution or adhered to surfaces, and cells in solution or adhered to surfaces. Now these NCQDs have a transition energy in addition to spectral regimes and have recently been developed. Now in particular there is indium arsenide or zinc selenide nanocrystal. So if you take indium arsenide on zinc selenide nanocrystals and lead salt semiconductor nanocrystal and lead salt, which includes lead sulfide, then lead selenide, or lead telluride. Have strong size quantized optical transitions in near infrared. Got strong size quantized optical transitions in near infrared region, the near infrared region. Fabrication problems have been solved with demonstration of mono dispersed colloidal synthesis. So that has to be a fabrication problem of these complex nanocrystalline quantum dots. So these fabrication problems have been looked into and solved with monodisperse, solved with monodisperse colloidal system. Colloidal synthesis. And the unique and novel quantum structures can be created by integrating different types of cell conducting quantum dots. So unique and novel quantum structures, volumetric QS, can be created by integrating different types of semiconductor quantum dots. These hybrid structures are being investigated for information sensing and processing in ambient solution environments. So the usage in ambient solution and environment is the key. Okay. Now, the next topic that we would like to focus on is the plasmonic nanostructures. So these plasmonic nanostructures can also serve as efficient couplers. They can be efficient couplers and from nanoscale to optical wavelengths, and using the quantitative predictive methods developed over the last few years, these structures can be designed to focus micrometer scale light into nanoscale volumes with high spatial and spectral control. So can be used to focus micrometer scale light into nanoscale volumes with high spatial and spectral control. With high spatial and spectral control. For example, if we talk about something called core shell dielectric metal geometries. Core shell dielectric metal geometries. Or plasmonic nanocells, they can be also called plasmonic nanoshells. these materials have been found to show sharp tunable plasmon resonance. So they show sharp tunable plasmon resonance. And that is why these materials are can be used as optical nano antennas, as optical nano antennas, let me call it as A, or can be designed for focus micrometer scale light into nanoscale volumes with high spatial or controlled concentrated energy. Bow tie nano antennas, there are something called bow tie nano antennas can be these bow tie nano antennas can concentrate light into 100 nanometer gaps. So these have the capability of concentrate light into 10 nanometer gaps with local field enhancement up to 10 to the power 4 with local field enhancement of order of 10 to the power 4. And apart from that, C-shaped metallic apertures possess similar properties. So the following property is also being shown by C-shaped metallic apertures. Possess similar properties. So let us understand what are these two properties. Now it has been shown that the silica, I should say, silica core gold shell nanostructure. We consider silica core gold shell nano shell, then they have shown resonance shown resonance as a function of the corresponding core shell ratio. like consider the intensity, what is the wavelength, this is the wavelength, lambda in nanometers. So a 20 nanometer shell will show a resonance like this, somewhere around, say, we consider this as 500 nanometers and this as 700 nanometers and this as 1200 nanometers. So it for 20 nanometer core shell. So this is for 20 nanometers. Actually, it's not that smooth. It's gradual. So this is for a 20 nanometer. And we have a, let's say, a 10 nanometer will show a lot like this. For 10 nanometer. Then 6 nanometer will blow or short like this. So what is happening is that as we decrease the size of the shell, the resonance is shifting towards higher wavelengths. So decrease shell size, it has resonance shifting towards higher wavelengths. So how the core shell is, we are changing the size. It is, for example, we can have initially we can have a solid nanosphere. This is not a core shell. So this is a solid nanosphere resonance. As we move to the core shell will look something like this. We'll have a silica core followed by surrounded by gold like this. So here the core radius would be 60 nanometers. And the shell radius, so this is for the core, and the shell width, I should call it, I mean this distance, it's 20 nanometers, the shell. So what we can do, these values actually they indicate the core or the shell width. So now, so this 20 nanometer corresponds to this 20 nanometer corresponds to this resonance peak. So now what we are doing, we are reducing the size of the shell. So increase the size of the core, that is, we have reduced the size of the shell. Okay, now 16 nanometer core here, this is the same. However, the shell size is now 6 nanometers. So we see a shift of the resonance peak. This is for the resonance peak for the shell type of structure. Coming to the bow tie type of antennas, these bow tie sort of antennas are like this. Okay, this is from the top, and if you look cross-sectionally, so they will have semiconductor structures like this.